My name is Eddie Harris, and I'll be talking about ATP pathways today. So we'll talk about the breakdown of one molecule of glucose into ATP, and also one molecule of palmitic acid into ATP. And so the pathway that glucose takes to become ATP, it goes through glycolysis, the Krebs cycle, and the electron transport chain. So glycolysis is the conversion of pyruvic acid into acetyl-CoA. In the Krebs cycle, there's a series of chemical reactions that allows for the oxidation of acetyl-CoA, and the electron transport chain allows for the transfer of electrons through a membrane within mitochondria to form a gradient of protons that causes the creation of ATP. And this is caused through a series of reactions that involve hydrogen ions and two specific coenzymes. So the coenzymes are nicotinamide adenine dinucleotide, NAD, and flavin adenine dinucleotide, which is FAD. So these two coenzymes form hydrogen ions to also produce ATP as well. And so it's quite similar to what happens with palmitic acid, except for the first step, which is beta oxidation. And beta oxidation is similar into glycolysis, and that is the fatty acid being broken down into acetyl-CoA. So acetyl-CoA is important because it's needed for any type of substrate, whether that's glucose or a fat like palmitic acid, to be converted into acetyl-CoA. And acetyl-CoA is what's needed for the Krebs cycle, or the citric acid cycle, as it's also known as. Okay, and so now we're going to look at a closer look at the breakdown of glucose. And so it starts with glycolysis, which is right here in the upper left. So glucose, right away, you get 2 ATP from glucose being broken down into pyruvate. So 2 ATPs right away. But once again, remember that hydrogen ions are combining with NAD or FAD. But in this case, they're combining with NAD in glycolysis to also form ATP. And it's 2.5 ATPs for every time hydrogen ion combines with NAD. So that produces 5 as a result of glycolysis. As we mentioned, we need the pyruvic acid to become acetyl-CoA. And so you have the pyruvate being broken down into acetyl-CoA. But as that's happening, you're still creating ions, hydrogen ions, that are combining with the enzyme NAD. And then so you're getting more ATP being created from the electron transport chain or system by way of oxidative phosphorylation. And so for every acetyl-CoA, that's one spin or one time around the Krebs cycle. So if there's 2, then you're getting 2 turns in the you're getting 2 turns in the Krebs cycle. And every time the acetyl-CoA goes in to the Krebs cycle, the same amount is coming out as ATP. And so that's the bottom number here that says 2 ATP. But once again, you're also creating ATP from the combination of hydrogen ions with NAD and FAD. So 2 total spins or turns in the Krebs cycle produces 6 of the NAD enzyme being combined with hydrogen ions, and that's multiplied by 2.5. And then the 2 turns or 2 spins in the Krebs cycle will produce 2 FAD enzyme and hydrogen ion combinations, and that will give you 1.5 ATP. And so you can see a lot of the ATPs being formed through this electron transport chain through the process of oxidative phosphorylation to produce ATP. And so all of that will give you a combined 32 ATP. And that's how the total ATP that's created from one molecule of glucose. And then we have palmitic acid, which is a fat. So the first stage, once again, is different. So it's not glycolysis, it is beta oxidation. And that's basically just breaking down the carbon chain of the fatty acid. So palmitic acid has 16, so you just divide that in two, and that will give you 8 acetyl-CoA, and that's what goes into the Krebs cycle. Unlike glycolysis, there are no ATP formed from this process. You actually lose ATP to start this whole process. But once again, much like glycolysis in the Krebs cycle with molecule glucose, you still have the electron transport chain creating ATP by the combination of NAD and FAD with hydrogen ions. So once again, in the Krebs cycle, acetyl-CoA will directly produce ATP. So there's 8 turns. That means there's 8 ATP formed as a result of going in the Krebs cycle. But then you can see as well that due to the electron transport chain and oxidative phosphorylation, that combining of hydrogen ions with NAD and FAD, that you're getting ATP created as well. And once again, the bulk of the ATP is being created as a result of oxidative phosphorylation through the electron transport chain. But palmitic acid, total, as we go through all the steps in beta oxidation, the Krebs cycle, has a total yield of 106 ATP. So the Krebs cycle, the ATP is pretty much controlled by the amount of acetyl-CoA. So however many acetyl-CoA you have, that's the amount of ATP that can be directly produced from the Krebs cycle. And then your electron transport chain is all about your NAD and FAD enzymes being combined with hydrogen ions. So you need those to produce ATP in the electron transport chain. And beta oxidation, once again, nothing comes from that, but that carbon chain will determine how many acetyl-CoA is formed, and we'll go through the Krebs cycle to create ATP. So pathway interaction. So a little bit about energy systems. So basically, there are 2 that are used from fat and glucose, or carbs. So the first one is the aerobic metabolism, which is with oxygen, and the second is anaerobic, which is without oxygen. So with fat, that is always with oxygen. So you can't create ATP from palmitic acid or fat without oxygen. So you need it. However, you can use glucose without oxygen, which is anaerobic metabolism. And only glucose can be used for this. Fat cannot be used for anaerobic metabolism. So at the beginning of a workout, if your intensity is low, then your body can use the fat to create energy. However, if your intensity increases, then your body has a hard time getting oxygen, so it has to rely on the glucose to create the oxygen. So that's where glycolysis comes in. So, and that can only be done with a molecule from glucose. Duration is the same. After a while, the body relies on fat. So at the very beginning, we'll use some carbs or some glucose to produce ATP, but glucose is limited, so it can produce ATP rapidly. It actually produces it faster than fat, but it runs out. It's not a large supply. So the longer an exercise goes, the more it's going to rely on fat. The shorter and more intense it is, the more it's going to rely on carbs or glucose to get that done. Okay. So what does this mean as far as exercise and movement? So when it comes to exercise and movement, you're going to rely on both systems to get the job done. So first of all, if you're exercising and you're running, however, and it's at low intensity, you can use your fat to create ATP to create energy. If you increase your speed and make it more intense, then it's going to rely on glucose to create ATP to get you through it. Okay, so if you're doing some type of exercise that requires power, you're going to need ATP that's from carbs or glucose. Okay, so ATP from fat, while abundant, um, it doesn't produce the same amount of power as ATP from carbohydrates. So, so yes, you want, if you did want to use the source that creates the most ATP, that is fat, absolutely, but it doesn't create the same amount of power. So if you want to do a sprint, and you can't rely on fat to do that. Dopamic acid doesn't give you enough of the power to have you sprint, which means run as fast as you can. That only comes from carbs. So that is why you can't just rely on the system that produces the most fat, because you need carbs. Glucose is what will help give you the power that you need. So um, different activities require ATP from different sources. All ATP is not the same. So in order to maximize your power, in order to go all out, exercise, you need to have carbs. You need the glycolysis to kick in, because that will help produce the power, whether that's sprinting or jumping. Max energy comes from that, whereas the maintenance uh, of an of an exercise or activity, a lower intensity, the ATP from fat will help produce the energy to do that. So that is the lecture on ATP, and here are the references. Thank you for your time.